Chump++, you already heard a little bit from Rusty, is a system that's been in use by a variety of applications. At least 5 applications running on NSS Track 1 machine, the most largest machine that NSF has, are actually Chump++ applications and so on. And I think I will really gloss quickly over the challenges. You all know that the applications are getting more sophisticated. You know that the machines, the applications now need to be strong scaled, not for several generations of parallel machines. Every time you give scientists a new machine, they would be able to just expand the resolution and occupy that machine. That's no longer the case. You're kind of, in many applications, you're at the end of that kind of scaling, and you want strong scaling to get the same size problem running much faster on bigger machines. At the same time, the machines themselves are becoming more complicated. They present all kinds of variability, static variability and dynamic variability and so on. Temperature issues, energy issues, they're all kind of complicating our life as programmers. So what the Chump++ approach is not full automation. It's not full burden on application developers, but rather it is a good division of labor between the programmer and the system. So how does Chump++ do it? Well, the first order, Chump++ is a general parallel programming model. It's not a domain-specific model. You can think of it as an alternative to MPI or UPC or Chapel and so on, but it's not an alternative to C++ or Fortran or something. It's not a language in that sense. It represents a style of writing parallel programs. It includes an adaptive runtime system, and it includes an ecosystem around it, which includes debuggers and performance analysis systems and so on. So there are 3 concepts at the basis of Chump++ that you should understand. So the first concept is over-decomposition. Over-decomposition is the idea that you decompose the work units and data units explicitly. It's not going to be automatic. The programmer is going to do the decomposition, but they are not going to do the decomposition to the number of processors. So that means they're going to make maybe lots and lots of pieces. If there are 1,000 processors, you may make 10,000 pieces of work, for example. So this is not so hard. You do decomposition anyways. You just overdo it. So that's first thing you do. And the second thing is at the basis of the system is you make these work units and data units migratable, right? What does that mean? That means the programmer does not think about the physical processor. So you address your communication to the logical entities, not to the physical processor, right? That's a good thing, one less thing to worry about. But for the runtime system, it's a little bit of a headache. It needs to keep track of where each unit is, and it needs to do naming and location management, which it does well. That's one of the things that's built into Chump++ system, so it knows where each object lives, for example. The third thing is asynchrony, and you have many units on each processor. Many objects are sending method invocations towards them. Well, they need to be scheduled. So the scheduling can be done under user control or under system control. And we say, no, not under the user control. User doesn't say, next run this, because the thing that you're talking about running may not have all this data available. So we say, scheduling, let it be the choice of the runtime system. The programmer only says what's available, and then the system picks what's ready to execute. This is called message-driven execution. Now, so these 3 ideas are realized in Chump++. The over-decomposed entities in Chump++ are called chars. Char is just an old English word for chore, but in our case, it means a C++ object. There are methods on objects, and some of the methods are designated as entry methods for chars. In fact, that's a distinguishing feature of a char. A char is a C++ object which also has entry methods. And entry methods are methods that can be invoked from remote processor, potentially from remote processors. So chars have entry methods. Chars are then organized into index collections. We'll come to, in the second half of the talk, to index collections, but each collection has its own indexing scheme. It can be 1-dimensional, 3-dimensional, sparse, or dense. And then chars communicate with each other via asynchronous method invocation. That means I invoke a method on this object. In normal sequential means I get a return value back. That method runs, I get a return value back. Here it means I send a method invocation towards that object, and at some point in future it will execute. All right, I continue doing other stuff. If it wants to give me something back, well, it will invoke another method in my object later on. All right, so that's asynchronous method invocation. So if you look at this picture, this is an ocean of objects. A parallel program consists of a whole bunch of objects. In case of Champ++, the program consists of sequential. Some objects are globally visible objects. Let's say those are globally visible objects. The other objects are just your usual sequential C++ objects, right? And so those sequential C++ objects are just owned by the globally visible object. One or the other of them will own it. And so in object orientation terminology, that will be a has a relationship. Each parallel object has a 1 or more or 0 sequential objects attached to it. They all move together. Now, if you just focus on the globally visible objects, then the runtime system is going to partition them. The user's view is just that of the ocean of objects. The runtime system is going to partition them into processors. In this case, I've shown only 4. And then it's going to say, okay, well, now I need to execute things. There's going to be a user level scheduler on each processor, and there's going to be a queue of method invocations that's waiting to be executed on each processor. So specifically what happens when you invoke a method, let's look at an example. The processor on the left, the orange one, let's say, wants to invoke a method in 23rd element of the object collection A. So it simply says a sub 23.foo and some parameters and makes that call. The runtime system says, oh, that's what you want to do. It will package up that into that little green packet shown there and serialize it, put the information there, and then figure out where that object lives as of now, sends it to that processor, and that packetized, that serialized message just sits in its envelope inside that scheduler's queue on that processor. At some future time, the scheduler, this packet comes to the front of the queue, it picks it up and says, hey, is the object still here? If it is not, it might have migrated away. I'll find out where it is and send it there. If it is still here, which is most likely the case, you invoke the method, let it run to completion, which will create more such method invocations for other objects, which will be sent towards their destinations, and the execution continues in that fashion. This is the entire execution model. Well, let me say one more thing. You then notice, the runtime system notices that some of these objects are fatter and some are thinner in terms of the computation load they represent, or maybe memory, maybe communication, and the runtime system is watching them execute, and then it says, oh, I need to move things around. I need to move work away from this processor. Oh, this object talks to more objects on that processor. So it can take communication into account, computation load into account, and move things around to effect optimization. So this is the entire execution model of Champ++. And this is something that's roughly, Champ++ came about in about 93 or so, the name, but most of the concepts are stabilized around 1998, 2000. So it's a really old model, but it is really modern in terms of its applicability. And it's kind of like an old idea, which was well ahead of its time, but now we need it. You'll see why. Once you have these 3 things, over decomposition, migratability, and asynchrony, and you add to it an introspective runtime system that can adapt to what's happening, you get an adaptive runtime system, which can do a variety of things like dynamic load balancing and so on. Let me show schematically here. With over decomposition and message-driven execution, you enable a variety of things like automatic overlap of communication and computation, compositionality. I'm not going to go into all of the details. With migratability, you can do fault tolerance. With introspection and adaptivity, you can do dynamic load balancing. You can do automatic power and temperature control. Just a couple of those concepts I will illustrate. So, for example, here, there is now a lot of activity around multi-cores, many cores, accelerators, and so on. Well, locality that objects connote, Champ++ objects, you work, an object is allowed to work on only its own data. Anything else it needs, it has to get it from method invocations. And so that connotes a locality, and that's always helpful on all of these architectures. More interestingly, message-driven execution, the scheduler has a peek at the queue. right? It knows what's the next thing to execute. It also knows what are the next 5 things to execute. It can prefetch the data needed by those. How does it know the data? Well, it knows the data because every object's data is that object's is all that is a method invocation is going to touch. And so it can prefetch data into, say, scratchpad memories or HBM, the high bandwidth memory from the DRAM. And so these kinds of movements can happen automatically because of the ability of the scheduler to peek ahead. You look at communication. If in a typical MPI program, well, somewhat caricatured, you get compute, communicate, right? Represented here by the red and white. You actually might say, well, I'm spending 30% time on communication, and if you understand some of these optimization techniques, you might move some sends up, use I receive and wait alls, and so you will say, well, now I'm using spending only 10% of time in communication. You're happy, but really you are wasting the communication network 90% of the time. Isn't that what that means? And we worry about floating point utilization so much, why don't we worry about communication network utilization? So instead of reducing time on communication like that, what over-decomposition does is it spreads the communication over the entire time step, right? So one object does its work, sends its data out on its way, while another object starts executing, sends its data afterwards, and by the time you're ready for the next iteration, the first object already has its data from whoever is sending it. Some objects has its data, and it can continue working. So the communication spreads over the entire time step, and you get an automatic adaptive overlap of communication and computation. When we typically decompose problems in the traditional method, you decompose them to processors. Let me give you an example. So this is an example from a rocket simulation thing, but very generic, generically speaking, fluids and solids, right? And so typical thing is to partition the fluids mesh, which might be a structured mesh, into P pieces, partition the structures mesh into P pieces if there are P processors, and put the 17th chunk of the fluids mesh and 17th chunk of the structures mesh on processor rank 17, simply because their partitioner called them 17th. Right? There's no geometric connection between them, anything like that. And so instead, with Champ++, what you do is you decompose the solids mesh into maybe N pieces, but fluids mesh into M pieces. Doesn't have to be the same. And they are just logical decompositions. They talk to each other. The runtime system figures out whether they should go on, which one of them talk to each other more, which one execute concurrently or one after the other, and accordingly figure out what lives on which processor. Right? So you are freed up from that task, and the system can optimize things better. So then Champ++ is a way of parallel programming based on objects, over-decomposition, asynchrony, migratability, asynchronous method invocation, which is the messages, and an adaptive runtime system. So here is, we're going to jump straight into some syntax, and then for the next 20 minutes or so. So here is a hello world program, very simple one. You write a .ci file. I'll explain what the .ci file. A small .ci file, it's an interface description file in addition to your C++ program. So here is your C++ program. It has a class called main, and it has only the constructor, which has to be by definition an entry method called main. And so you declare them in the .ci file. Hey, I have a class called main. It happens to be, I have a char called main. It happens to be a main char. A main char is a char that gets created at the beginning of the computation. So the whole Champ++ computation begins by creation of one object, a main char, somewhere, typically on processor 0. And so you have to tag a char as main char so that the system will automatically create one instance of it somewhere. It has an entry method called main, and the whole thing is wrapped inside a module. I will explain modules in a second. And then the class main is simply doing this, calling ckexit when it's printing hello and calling ckexit, and I'll explain the inheritance a little bit, and some of these include files here as well. So basically then a C++ program has typically a .h file and a .c++ file. A Champ++ program has a .h, .c++, and then in addition to help us do some of this serialization of method invocations, etc., you provide this .ci file. Once you have that, you can process of compiling a charm program, you use charm C instead of your C compiler. So you say charm C hello.ci, charm C.c hello.c, and then link them together to create an executable called hello. And then to run it, you typically, this depends on machine to machine, but typically you'll say charm run plus P7 hello. So it's running on 7 cores, right? What actually happens during that process is that .ci file, which describes the interfaces to your program, is parsed by the charm C translator. It's a very simple translator, and all that it does is it creates some declarations and definitions of derived classes based on what you declared there, which are included. So the class declarations are included at the top of your decal file, .h file. And at the bottom, the definitions are at the bottom of your .c++ file. And then you send that through your normal C++ compiler. You use charm C for that so that it knows some library paths to automatically include and so on. And then you create your .o, link that into an executable. So now let's cycle back and explain what some of those constructs that you saw in the main Hello World program. You saw something called module. A charm++ program is organized as a collection of modules. So each module can contain one or more char classes. The module that contains the main char is also declared as a main module. So for now, just take it as that's what you have to do. If you include a main char, then you must be a main module. And let's see, each module when compiled produces the decal. And so if the module name is my module, then it will create my module.decal.h, declarations, and my module.def.h, right? And so, well, that's how the syntax of that in .ci file is: module, name of the module, open curly brace, close curly brace, semicolon. So, and inside of that, well, there could be char definitions. So chars. Chars are parallel objects, as we said before. Chars may have one or more entry methods, and so their implementation is in the .c file. So in the .ci file, what you see is char, name of the char, and if it happens to be a main char, then you just tag that prefix main, and then inside are entry method declarations. What's an entry method? Well, you say entry, name of the method, and so if you have a class called char called myChar, then it has to have a constructor, which is also an entry method because it can be created remotely, right? And so, and then it has other entry methods. The entry methods can carry parameters, and you have to declare them. The reason you're doing this in .ci file so that the system can see those parameter declarations and generate the appropriate serialization code, right? So in the .ci file, you write those entry definitions inside a char, and then in the .c file, you just write regular, so my char : foo, my char : bar int param, and just the code to execute. So the actual C++ code in your .c file as usual, and the .ci is simply a little summary of what signatures exist for the methods that may be remotely invoked, essentially. The main char constructor takes, in C programs, you have this argc, argv, the same concept. The main char constructor gets the argc, argv in the form of a structure which contains an argc and argv as two fields in it. And then now let's look at how you create these chars, right? So remember, for every char class called myChar, the system is going to not remember, I didn't explain that before. The .ci file processing generates the declarations of additional classes. So if you declare a class called myChar, it's going to create a class called cproxy_mychar, right? And so where it is used, etc., you'll see only by examples. But here, that proxy class is used for generating a new member. If you're doing sequential C++, you want to create an object, you just call new, right? New class name, that's it, and some constructor parameters. That won't do, because if you do that, you create a sequential local object not visible to the runtime system. So instead, you say cproxy_mychar : ck_new. Now the system knows, because it generated that cproxy class, right? It knows, hey, you want to create a system visible object. So it will create that object on some processor of its choice. You don't know where it is going to be created, and will manage that object, know where it's located, and so on, right? And pass the arguments to it, etc. You want to, in future, communicate with this object. That can be done. For that, you need to retain a pointer to it. And the way you retain a pointer to it is by taking the return value, which is a proxy. So cproxy underscore mychar, that's the same class name, that's the proxy you will get back, right? And so you get a pointer to that object. It's not a pointer in the usual sense of the word, not the C++ sense of the word, but it's a globally visible handle to that object. That's what a proxy is, a globally visible handle to an object. So cproxy underscore mychar proxy equals cproxy underscore mychar cknew constructor arguments. That's how you create an object. So we'll look at one example here. This time pay more attention to the syntax and see if you understand it. You have hello.ci file. This contains the module name is hello. File name is hello also, but that's not necessary. It's the module name that will decide what the decal file is called. This module contains two chars, main and singleton. Main is the main char, and singleton is just a regular char. Okay, and so each one of them has an entry method, which is the constructor entry method, and that's all that we're declaring here. If you look at the .c++ file, you have at the top include hello decal.h. That hello is the name from which this is derived, and that's where all those proxy classes, etc., will be constructed or created by the system, and their definitions are here at the bottom. And then what is it doing? Well, the main object, when it gets created, it doesn't look inside the arg message. It doesn't need that. All that it is doing is creating a new object of type singleton by calling cproxy underscore singleton : cknew. Makes sense? So it created that object on some processor. If the system is running on 100 processor, one of those 100 processors, the system will create that other object. You don't know where it is. You don't need to. And then that object is going to print hello and call ckexit. Now, why ckexit and not exit? Because if you call exit, that process will go away. But that's not what you want. You want the entire parallel program to exit. Remember that picture with all those different processes and schedulers of their own on their own processors? Well, all of those guys need to be told that, hey, the program is ended, go away. Otherwise, they're choosing to sit there waiting for something to happen till the end of the world, right? And so, no, you have to tell all of them that the program is exiting, and so you call ckexit, right? Okay. This is this is a good program to see all the basic components. You can compile and run this program. Now let's look at a little more detail on some constructs. I think I talked about proxy. When you create an object through cknew, the return value you get is the proxy to that object through which you can invoke methods on it. But there is another way of obtaining that proxy. You can obtain your own proxy. It's like, I'm an object. What is the pointer to me? Well, that's this. In C++, it's the special variable this, right? Well, but that's just a sequential pointer. But if you want a global handle for an object, you say this proxy. So this proxy will give you a handle that you can pass to other objects as parameters. So then they have a handle to you, and they can invoke methods in you, right? And here, for example, I get a handle to the main object, well, some object whose name is main, and so then I just say main.foo, that will do an asynchronous method invocation on that object. Make sense? If it were a regular pointer, it will be main.foo will just be a local call. It's a globally visible handle to an object, so it's an asynchronous method invocation. Here is a slightly more complicated example. Again, you have a main module, has main and a simple char, but this time the simple char is not just going to, it has some parameters now. It's not just going to call print hello and exit, but it has an int and a double as a parameter, okay? And so in the .c file, you have a main class, and notice one other thing that has been coming up before. Let's explain. Main class is now subclass of every class that you have that's a char class. In the C++ file, you must declare it as a subclass of C base underscore that same class name. Where does this C base come from? Again, the .ci file processing is where it comes from. So it goes in the decal and defs. So when you told the system, hey, I have a char class called main, it created a C proxy underscore main, it created a C proxy underscore, C base underscore main, and so on, actually, a couple more. And so it has to be a subclass. That's how you get this proxy, for example. You inherit from that guy. Okay, so then this main is saying hello world, and then it's saying, hey, pi is, according to me, 3.1415. We know that's not correct, but that's okay. And then, well, not accurate at least. So, and then it's going to pass the pi to the simple object, a newly created simple object, and the first parameter is going to give is 12. And I think that object is supposed to do something like print the area of a circle. So simple will simply say, oh, I got y, which is the value of pi in this world, and so I'm going to calculate pi r square, and I'm going to print the area of circle of radius 12 is such and such, and it prints the answer, and then it says done. That's all we needed to do. That char calls ckexit. By the way, why does main char not call ckexit? Well, it could. You'll have to call a method back into it, and then it can call ckexit. But since ckexit is a symmetric call, that is, you can make it on any object on any processor and will shut down the entire system, then there's no need. If you know this is where the computation ends, you just call ckexit at that point, at the point where you know that the computation is ending. All right? Now, pay attention because a puzzle is coming up. So, now you have cknew call, and the entry methods are asynchronously invoked. So for example, if you have a proxy to an object of type mychar, and you're invoking a method foo, and you're invoking a method bar on it from some object, right? Some object comes and says proxy.foo, then it says proxy.bar. What order will those methods execute on the target object? First foo, then bar? Not necessarily. The asynchronous invocation scheme means that those things go and sit in the scheduler's queue. You might have associated priorities with messages. The messages might get delayed in the queue. We don't, by default, guarantee any ordering between messages. So maybe the bar will execute first and then foo, right? So whichever one comes to the head of the queue first, it will execute. All right. One other thing is that only one object entry method of an object runs at a time, which ties an object to a core, basically, right? So if it is running a method, then it's not like some other core is going to run another method for the same object, right? So that's what the second bullet is saying. Yes?
So the char once created, you said it can migrate?
Yes.
So it's possible for foo and bar to actually execute on two different cores if the char migrates?
They will follow where the char goes.
It's not even guaranteed that the two will execute on the same target, wherever the object might have migrated. So foo might execute on...
Yes. Yes. If foo comes and, well, let's say bar comes first and meets the object on processor 23, and then foo follows along, comes to 23, but the object has migrated to 15, well, it will go to 15 and execute there, okay? Objects don't migrate that frequently. They migrate for load balancing. So keep that in mind, but in principle, yes, it will execute wherever it is. Okay, I think this is illustrating the same thing. You say foo and bar, the print inside foo and the print inside bar can occur in any order. First foo, then bar, first bar, then foo. Now let's do another example and then the puzzle at the end of that. So the same idea that there is a char called simple which has a function called find area which is given a radius, and this time we say, well, come on, we know pi, we don't need to send it. And so instead we are passing a second parameter called bool, done. And that parameter, the idea is that you say, hey, I'm done, no more problems for you. So here is what the main char is doing. The main char is constructing an object of type simple, getting a proxy to it called sim. Then in a loop for I going from 1 to 10, sim.findArea I false. So it's saying for first 9 values, it's saying find the area of a circle of radius 1, of 2, of 3, and so on. And then it says sim.find area of circle of radius 10, and with the second thing as true, meaning I'm done now, right? And so this thing is the simple object constructor does nothing much. Object is constructor is simply doing y equals pi. Well, in this case, that's not necessary. I don't know why. Oh yeah, the constructor was given pi. Yes, we didn't say pi. And then find area is given a radius and a Boolean done. So it calculates the radius, prints the calculates the area, prints the area, and then if done is true, then calls ck exit. All right. Now tell me, does this program execute correctly as intended? Will it print any kind of mixed up squares, areas, like, oh, the area of circle of radius 1 is 4? No, because the method invocation has both of them tied together, right? The radius comes and you print the area for it. Any other problem you see? If they execute out of order, then on the 7th one might be the one that says done is true, and the other two, like for 8 and 9, are still kind of waiting in the queue somewhere, in the message queue, and the last one comes first and says, oh, 10, true, done. And so you call ck exit, not giving a chance to the other methods to run, right? So how to fix this? Well, this kind of asynchronous programming is what gets you when you start programming Champ++, but it's a little bit of time to get used to it, but then it becomes second nature to program to the correct way of doing it. I leave it to you to think about how you will write the program so that it behaves correctly. A simple thing would be to send a count, for example. So you can pass any types of parameters. If you're passing something like an array, int data square bracket length is how you'll declare it in the CI file, and here it is just int star data as usual. So the system knows how to package that information and send it off. That's the only additional thing. Other than that, the .ci file should be as usual. Yes?
What happens if my char is having memory and it's moved to a different node?
What happens when your char is what?
So in my object, I allocate memory, and then I move off to a different.
When you move, you get a chance to package your data. There is a pup method that you have to write that will package your data and take it there. And so a lot of it is automated, but some of it is you have to help the system a little bit there. Okay, so the collections of objects. Objects can be grouped. So far, we just had these chars, and you can create networks of chars by explicitly passing proxies. It's not as convenient. A useful thing is to define collections of chars. And so these things could be like blocks of matrices, chunks of unstructured meshes, volumes of simulation space. Those could be chunks. They could be more abstract than that too. But structurally, what you get is that you have 1-dimensional, 2-dimensional, 3-dimensional, up to 7-dimensional arrays, or they can be unstructured, anything hashable. You can have bit vectors, you can have strings as indices by which to refer to char objects. They can be dense or sparse. You can have an array, a collection of objects that goes, which is a 1-dimensional index that goes from 0 to a trillion, and only 10,000 of those trillion exist actually. So you can have sparse or dense, and you can have static, everything created at once, or you can even insert new members into a collection as you go along. So declaring an array, you can declare it as shown here. Array instead of saying char foo, you are saying array 1D foo, which is saying you have a collection of 1-dimensional collection of chars. Again, class name is still foo, and you have some entry methods and so on. And then in the C file, you would do as before, struct foo public C base underscore foo and so on. Constructing a char array, it's ck new, but with one twist. You provide an additional parameter, which is the size of the array. So this one says create a collection of foo objects of size 10. This one says create a 2-dimensional collection, because bar was declared 2-dimensional, 5 by 5, right? And so again, when you create it, you can still retain the proxy to that object. And if you say my foo dot method 1, what do you expect to happen? You created a collection, and that collection has a name, myfoo, and you say myfoo dot some function and some parameters. Just a natural expectation. It's not, I didn't teach it, so just tell me what you expect.
So it executes it on all chars?
Executes on all chars. So it's in effect a broadcast, right? So you send that method invocation to all chars. If you want to send it to a specific one, then you specify the index and then dot foo, right? So myfoo.for dot invoke entry is how you will do the invocation there, right? This index, instead of this proxy, this proxy gives you a proxy to the whole collection. This index gives you my my index. If I'm a one-dimensional array, that's just my index. If I'm a two-dimensional array, then this index is a struct, and this index.x and this index.y will give you my x and y coordinate, or first and second coordinate, right? And so on for the other dimensions. All right, so here is a simple example, again, a different hello program. You have a main char. It's going to create a collection of hello objects. One-dimensional hello is a one-dimensional collection, and it has a method called print hello. So what that's going to do is the main one simply says cproxy hello colon ck new array size. So that's going to create a collection of, array size is 100, then 100 objects spread over your 17 processors, whatever number of processors you have. The system is figuring out where each one of those 100 objects lives. You don't care, and they're created, right? And then you tell here p sub 0, p is the name of the proxy, and so you say proxy to the whole collection, p square bracket 0, the 0th member of that collection, print hello, right? And what does that do? Well, that print hello method says, I got hello from p sub whatever my index is. This is this index. And you can also say I'm running on my processor. You can ignore processors most every places, but you have a function call available to say which processor is this running on, ck my pe. And then you send it to, if I have reached the last element, then I exit, call ck exit, the program exits. Otherwise, this proxy square bracket, this index plus 1 dot print hello. Send to the next guy the hello message, right? So the hello message is going to travel from 0 to 1 to 2, 3 all the way to the end, and then the whole program is going to terminate. This is what it looks like logically. Physically, it might be a bunch of processors that it is spread out over. So to see that, you can just add dash trace mode projections, and there is a very sophisticated, nice performance analysis tool that this is only a cameo of that, and through that, so it will just create a bunch of log files. You run projections afterwards, and it will show you what happened in the program. Method invocations passing through processors and which object is running what. You can mouse over one of those blocks and see what that was, when it ran, what messages generated, etc. So the runtime, what it is doing is that it provides a service to find the objects efficiently, that is given a collection and index, where does that object live? You can influence that by writing a mapping function. They can be static or dynamic. This actually means that you can test the logic separately from their distribution. You can just write the program in terms of the object and say, I want to control their mapping, or I want the dynamic load balancer to control their mapping. And that can be a separate process. Broadcast looks like this. This proxy.foo sends to everyone. And reductions are slightly more involved because they are asynchronous. MPI nowadays has asynchronous reduction. Champ++ right from the beginning had non-blocking reductions. You can do the normal sum, max, concatenation, etc. But the way that's done is through a call called contribute. And the result of that contribution goes to some entry method. Right? In Champ++, everything has to go to an entry method. And so that entry method is tagged, especially in the .ci file, saying, hey, this method called done, it's a reduction target. You just have to say this method is a reduction target. And so this element, inside this element, you might do a call, a contribute call, and in that contribute call, you contribute some value, which in this case will be, some value which is this index in this example, and then it's a sum reduction, sum int, and then there is this little thing called callback here. So callback specifies where the result of the reduction should go. In MPI, you make the reduction call, the reduction result comes right there back to you, right? Here, it's an asynchronous model. You contribute into a reduction, and you can keep doing other stuff. So the result has to go somewhere, and so you specify that callback here. I wouldn't go into the details of the callback, but in this particular case, the callback is this done method here, right? And so that's where the result will go after the reduction is completed. So chars, what we saw about chars so far is reactivity. That is to say, a char, if you think about it, what does it do? It just sits there. If a method is invoked on it, then it does this. If that method is invoked on it, then it does that. Right? So it's very reactive in nature. But in fact, our parallel programs are not naturally reactive. They have a life cycle. If, not always, but if they have a describable life cycle, then we should be able to describe it in a much nicer notation, which is what structure dagger gives you. So I'm going to be somewhat quick, so let me just explain through one example here. So you have so the structure dagger code is like a script. You write that script inside your .ci file. So you have an entry method called some method, some portion, and that method has a code inside of it now, instead of the code being on the .c file. And what does the code say? It says serial. That simply means it's a C++ code here, just execute it blindly if you come to that point. Then when this entry method execution comes, then execute this block of code. When that entry method comes, execute that block of code, and that's serial. It could be recursive. It could be another set of when blocks here and other structure dagger construct. So you're basically describing a DAG between computations and incoming method invocations through this notation. And it tends to become, so this is a little bit like your receive in MPI, but confined to objects, not processors, right? And so you can write all kinds of interesting code with this. Not everything, but for example, you can say when method 1 and method 2 arrive, execute this block of code, right? So it's when M1 comma M2, execute this block of code. And you can attach reference numbers to it, just like tags. There is overlap statement, there is if then else statement, there is a for statement, there is a while statement, and all of these are defining flow of control within a single object. So once you master the basic Cham++, the next thing to do is to look at structure dagger and to be able to express, constrain the concurrency and express the life cycle of it better. Let me then show some examples of how you go about designing Cham++ programs. So the first decision you have to make when you write a Cham++ program is grain size. Let the programmer decompose their work, we said. How much over decomposition? So this should be coarse grained objects. You don't want every float to be an object because we don't have a compiler automatically doing some optimizations there, right? So you don't want small talk like objects there. So you're not going to magically collect or decompose things. You are going to make choice of the grain size consciously. So what you do is you choose a grain size, but it's very easy to parameterize the grain sizes for you. For example, here is a crack propagation example long time ago, 14 years ago. They were running on 16 cores. And instead of running on 16 cores with 16 processes, 16 ranks, we said, well, let's have 128 chunks, all right, 128 chars. So that's the kind of over decomposition that you do. NAMD, that's a well-known application of Cham++. On Blue Waters running a 100 million atom simulation, typically on 128,000 cores, it created like 5.5 million objects. That's something like 8 times 5, 44 or so objects per core. On a system with 4K cores running only a 92,000 atom simulation, it created 33,000 objects. So that's the kind of grain size you tend to do. Another example is a student came from Brazil, and they had in Brazil a version of RAMS code that they use for weather forecasting there. It's a production use code called BRAMS, and this was converted to Cham++ via something called adaptive MPI. And you can see that as a storm passes, the 64 processors processors used by their system, some of them get overloaded. As moisture is there, you need to do more computation. And so this load imbalance keeps shifting through the domain. All right? By decomposing the program into 1,000 virtual objects, 1,000 chars, they were able to, the system doing load balancing as the load passes, they got pretty good performance. So that's the kind of grain size deal that you have to do. And so the basic idea is that the grain size, if you make it too small, then the overhead shoots up on the left side. If you make it too large, not enough parallelism is available. On many processors, you'll get this thing where it approaches one processor at that point. Well, but there is this big range in the middle where your grain size can be anywhere in that bathtub bottom, and you're okay. Right? And so your idea is to be as left as possible on that to the extent possible so that you have lots and lots of pieces available for the runtime system to work on. But it's not very difficult to do. You just put a parameter for the grain size in your code typically, and you just kind of experiment with it in the earlier runs, and you know what's a reasonable grain size for it. You just need to be reasonable, does not need to be perfect. Here is an example of some 5-point or 7-point stencil. And we found here that 256 objects per core with about 2 megabytes per char turned out to be the sweet spot towards the left end. And you can see the flat region to the right of that again. So make it as small as possible, but as long as it amortizes the overhead is the real rule. Let me just show you a few case studies. NAMD is an example. And these case studies are important not just as an example of application, but to see the structure of chars there, right? So NAMD is a long-standing collaboration with Klaus Schulten. 50,000 nodes, more than 70,000 users now. And that was one of the recent, was in 2.5 years ago, success story of HIV capsid determination. The basic idea in NAMD is that you have a bunch of atoms and it's doing explicit but not quantum, classical molecular dynamics. And so in every step, you're calculating forces on every atom due to all other atoms. Far away atoms will be too many, that will be n square. So it is approximated using a particle mesh Ewald method. But if you ignore that far away atoms for the sake of discussion, you're calculating non-bonded forces and bonded forces on atoms. Now, so the challenge here is that you really have very small number of, relatively speaking, atoms to spread over a very large number of processes. They want to do really billions of time steps. So the way this was done in Champ++ was to decompose. Well, actually, let me show you this picture. You take the sets of atoms, decompose them into cubes, right? Such that you need to interact only with the neighboring cubes. The way that you avoid the distant interactions is by specifying a cutoff distance. And so you make the size of the cube to be a little bit more than the cutoff distance. If you do that, then you have those objects, the bricks, brick-colored objects there, and then you have non-bonded calculations. For every pair of nearby objects, you create another object whose job it is to calculate forces between them, and you have bonded computation objects. So you have kind of these multiple collections. Each one of them is a char array, in effect, right? And so you have particle mesh Ewald, that itself is another set of chars and char arrays. So you have multiple char arrays spread out over the processes by the runtime system. Most of the computation is in these purple objects there, 90+%, and the load balancer then takes charge of those and moves them around as the computation progresses. So this design has been going on since the mid-90s to now with some only modest modifications because the basic soundness of the method based on isoefficiency analysis and of this formulation using Champ++. I won't go through this nice picture, but it's a time profile. X-axis is time, Y-axis is a bar showing what activity is happening on different processors, and that's another one of those things that you get with Champ++, the projections tool. And excellent scaling to large number of, more than 500,000 processors. Changa is a parallel gravity application. And this includes both smooth particle hydrodynamics and n-body tree-structured gravity. It's kind of Bond-Sut with some multiple expansions added. And octrees are very nice structured geometrically for this algorithm, but octrees are bad for load balancing. And we say, ignore that. I mean, forget the fact that load balancing is our responsibility. Just decompose the objects as you find natural for your domain, and let the runtime system do the load balancing. So this is one of the challenging applications to parallelize effectively, especially when you have clustered data sets. Some regions of space are almost empty, where other regions are highly dense. And so on that as well, we have some very good speed up. Episyndemics is a simulation of a contagion over dynamic network consisting of people and places from Virginia Tech, Madhav Marathe and Keith Bissett and other people's work, done using Champ++, done first using MPI, then they converted to Champ++, and in fact, because of the asynchrony and the mappability, they got significantly improved performance with Champ++. OpenAtom is a Carpernello-based quantum chemistry program, so structural electronic structure program. This is collaboration with Glenn Martina and other people, and this also this shows importance. Actually, this shows a couple of things. The number of char arrays, the collections of chars that we talked about, this one has more than a dozen different collections of objects. So you have reciprocal space, real space probability density function, its reciprocal space, and several such different arrays, more than a dozen different char arrays, and they can be mapped in topology-aware manner by first doing the decomposition, making the program to work correctly, then specifying the map, experimenting with the mapping in different ways. There is a large number of mini apps, some of them just a few hundred lines of code that you can, if you want to understand the model better, just go to champ++.org/mini apps, and you'll find many of these applications that scale very well, and just in a few hundred lines or sometimes a couple thousand lines show you how Champ++ is used in practice. There is a book that shows the Champ++ applications, shows off them, and Champ++ can be used interoperably with MPI, with OpenMP, and there is a system called Adaptive MPI through which you can take an existing MPI code, pretend each rank is implement each rank as an object, and over-decomposed MPI in that fashion, and so run it with load balancing and so on. I didn't touch upon exascale issues, but we can do resilience. If you just add one call, if you kill a process, the system will detect the buddy processor, get the object data, spread it out to other processors, and continue running. It can do dynamic load balancing through one call. It can do power management. I will just state in one small example how you save cooling energy. Of course, cooling energy is very easy to save. You walk up to the thermostat, turn up the thermostat. You save cooling energy. But I don't think the machine operator will not kill you in that case. But the reason is that the chips are getting hot, right? Well, you monitor the chip temperatures. The particular chip that gets hot, you reduce its frequency. It cools down, but now you create load imbalance. Hey, that's a problem we know how to solve. Migrate objects away from that slowed down processor and continue running. So we actually can regain the performance at a fairly higher temperature by just monitoring the chips that are getting hot and dealing with them, for example. I will stop with that. Champ++ embodies an adaptive introspective runtime. Many applications have been developed using it, and basic signature strength is adaptivity, which is now even more useful at exascale.
So how would the use of Champ++ change my use of large-scale libraries such as PETSI?
Yeah, so this is where we got into this interoperability. So far, I mean, one answer would be no, right? Everything in Champ++, no. But no, you have huge, big codes written elsewhere. And so MPI codes, libraries can coexist and cooperate with Champ++. In particular, what that means is you start as MPI program, at some point fire off a Champ++ module, let it do its work, come back to MPI, continue its work, and so on. So you can work in that fashion. Yes?
If I do a remote method invocation on a chart, is there any way for me to know when that method is complete?
No.
That?
There is a way, but that simply not automatically. That object has to send a method invocation back to you.
How does it know who sent the message?
You'll have to put your proxy in that as a parameter, or some other implicit way of communicating that.